Hello, I'm Sylvia Knight, Head of Education at the Royal Meteorological Society. In this series of short films, we're going to be covering some of the background information that teachers may find useful if they're teaching weather and climate at secondary level, and specifically if they're using our weather and climate teaching guide with accompanying classroom resources, which can be found on our website, MetLink. In this film, I'll be looking at air masses. Air masses are a nice, simple way to start thinking about where our air has come from and what has happened to it before it reaches us, and what that means for our weather. However, it can be easily oversimplified and bear little relation to the current situation where pressure systems and fronts are probably having a far greater impact on what is happening outside the window. For example, on the day shown in this image, tropical air is covering all of the UK, but the high pressure is actually contributing more significantly to the clear skies seen by some and the significant fog experienced by others. An air mass is a large body of air with relatively uniform characteristics such as temperature and humidity. Air masses are classified according to their source region and their track. The source regions tend to be semi-permanent anticyclones associated with the sinking regions of the global atmospheric circulation in the subtropics and in the polar regions, giving us tropical air or polar air respectively. Air masses acquire the characteristics by contact with the underlying surface in the source region and the surface they pass over before reaching the UK. Fronts mark the boundary between two distinct air masses. When high pressure sits over the UK, there is usually very little air movement into the area and air masses are less relevant. Teaching about air masses usually starts with this diagram, showing that the air can approach the UK from pretty much any direction, and that the characteristics of the air depend on where it has come from. There are 6 air masses which can affect the weather in the UK. Polar maritime air is the most common, but we can also experience tropical maritime, polar continental, and tropical continental air. The UK sometimes also gets Arctic maritime air, which has travelled straight south from the Arctic. It's extreme polar maritime air, basically. Returning polar maritime air is basically polar air, which has changed direction over the Atlantic, hitting the UK from the west or from even slightly south of west, but still polar in nature. So a note of caution about this figure. It can be misinterpreted as showing that the northeast of the UK always experiences polar continental air, the south always tropical continental air, etc. In fact, unless there is a front in the way, we would expect one air mass to be affecting the whole country. The weather it delivers may be different in different places, more on this later, but on the whole, the cause, the type of air mass will be the same. This windrose for the East Midlands is typical for the UK. You can see that it records winds blowing from all directions, but most of the time the wind comes from between the west and the south. Our most common air masses are polar or returning polar maritime air and tropical maritime air. Arctic maritime and tropical continental air are really quite rare. We can compare that windrose with one from the Shetland Islands, where the winds are often much stronger. You can see that the directions are also different, with southeasterly winds being recorded more frequently. So now let's consider the air masses in turn. Starting with polar maritime air, this is air that has flowed out of a high pressure region in the Arctic to the northwest of the UK and arrives at our west coast from around the west or slightly southwest. As the air started off in the Arctic, it was initially cold, but then it warmed as it travelled south over increasingly warm waters. As the air temperature rises, you'd expect it to have a greater tendency to rise, so you'd expect to see convection, which is warm air rising. The clouds we associate with convection are cumulus clouds, puffy clouds in which you can often watch the rising air currents changing the cloud's shape on a fine day. As the air passes over the ocean, it picks up water vapour, so there will be cloud and rainfall out at sea, and then over the first bit of land that the wind meets, the west coast. The wettest inhabited place in England is Seathwaite, where rising polar maritime air is pushed further upwards by the Lake District Mountains. Annual rainfall at Seathwaite is about 3,552 millimetres. Crib in Wales, another mountainous region near the west coast, receives over 4,600 millimetres of rain every year. This satellite image is typical for polar maritime air, with puffy cumulus clouds over the Atlantic to the west of the UK and a more solid bank of cloud over the west coast, where air that was inclined to rise anyway is pushed up further by the underlying hills. Returning polar maritime air is air which originated in the North Atlantic but which was diverted before hitting the UK, so may approach from south of west. However, its characteristics are polar, not tropical. Arctic maritime air is very similar to polar maritime and brings localised snow showers across the UK in winter, predominantly in the north. As the air moves south across the country, it's warmed by the ground underneath, and the topography can trigger localised clouds and snowfall. Polar continental air will similarly be cold to start with and will get progressively warmer as it moves south, so you would also expect convection. However, the air will be very dry as it passes over Siberia and continental Europe, so little cloud will form. The UK is a set of islands though, and to reach us, the air must pass over the North Sea, picking up water vapour as it does. The longer the path the air takes as it crosses the North Sea, the more moisture it will accumulate. The cloud and precipitation, which is typically snow in winter, it brings therefore primarily affect the east coast. This satellite image is typical for polar continental air. You can see the cloud-free areas immediately to the west of the land masses, so for example off the west of Scandinavia, with cloud forming further east. The Beast from the east in 2018 was an example of polar continental air mass meeting a depression, which was Storm Emma, and that obviously resulted in widespread snow. The processes at work in tropical maritime air are a bit different. This is warm air which is being cooled from below as it moves north. You therefore wouldn't expect any convection with air rising, cooling and forming cloud that way. However, the air is being cooled just by moving north, and so it may eventually reach the temperature at which cloud forms. In this case, it'll be flat, featureless sheets of stratus cloud, because on the whole the air is staying at the same level. As it's maritime air, there's plenty of water vapour available to form cloud droplets. The processes which give us big, fat raindrops are mainly associated with the vertical air motions and circulations in cumulus and convective clouds. So tropical maritime air at best gives us a persistent drizzle. This satellite image shows the extensive sheet of stratus cloud over the Atlantic associated with tropical maritime air. In the UK, the weather fronts associated with depressions usually separate polar and tropical maritime air. We rarely experience tropical continental air that flows up from the Sahara over continental Europe. If we do, it can bring Saharan dust with it. This is the warmest and driest air we can get. Any moisture picked up over the Mediterranean will be rained out before it reaches us. So tropical continental air gives us clear skies. In the summer, this can mean that some areas get particularly warm, maybe because of their dark colour or their aspect if they're facing the sun. So this can cause very localised convection, giving rise to late afternoon localised thunderstorms, ringed in this image. In the winter, the oceans are warmer than the land, giving rise to more convection over the ocean. In the winter, there's also much less diurnal variation in temperature than in the summer, so snowfall, for example, is equally likely by day or by night. Of course, the characteristics of the air masses can be very different in the summer and the winter. Siberia, for example, is extremely cold in winter but relatively warm in summer. So a polar continental air mass can bring us bitterly cold weather and heavy snowfall for eastern counties in the winter, but much warmer weather in the summer. Using a synoptic chart, it should be possible to work out the wind direction and therefore the air mass. Bearing in mind that the air blows along the isobars, the pressure contours, then the task is simply to work out which way the wind is following the contours around the map. And it shouldn't matter which pressure system you consider, the wind should be able to blow across the map around the low pressure systems in an anti-clockwise direction and the high pressure systems in a clockwise direction. So if we look at this map where arrows have been added to indicate the wind flow and ignore the fronts, following each pressure contour, the wind should blow along the contour from one side of the map to another. Fronts mark the boundary between two air masses, and the image below is typical for a mid-latitude depression with a swathe of tropical maritime cloud caught between the warm and cold fronts, and the isolated cumulus clouds typical for polar maritime air evident both to the northeast and the west of the UK. Earth.nullschool.net can be used very effectively to investigate the current air mass, showing both the current airflow, the surface temperature and the mean sea level pressure. And again, you can see how the airflow is along the pressure contours. In the next film, we'll introduce air pressure and look at how differences in pressure can lead to air motion, so wind, and how rising and sinking air can lead to low and high surface pressure, respectively.